Alright, so I'm not going to go through the entirety of Lecture 17 since we covered a lot of it in class on Thursday before the break. So let's just keep on going here, and I'll just remind you of a few things. We were talking about divisibility, right? So if we have integers a and b, right, we say that a divides b, or b is a divisible by a, or b is a multiple of a, or a is a factor of b. But what we mean by that is that b is equal to a times another integer, right? And so if there is some integer k such that a times k is equal to b, then we'll say that a divides b. This is not a fraction. This is not saying a divided by b, right? It's not saying that. This is completely different, right? This is saying a divides b, which is a proposition. Yeah? This is either a true or a false statement. Okay, so yeah, just very important not to get that confused. Now, right, this is an example of how 3 divides 12 and 4 divides 12, because 3 times 4 equals 12, so 3 times an integer is equal to 12, and 4 times an integer is equal to 12. So here are some properties of divisibility, right? If a divides b and b divides c, then a must also divide c, right? And we went through the proof of that in class. If a divides b, then a also divides b times c. If a divides b and a divides c, then a divides the sum of b and c. Alright, so we could use divisibility to redefine what it means to be even and odd. So we'll say you're even if 2 does divide n, and we'll say you're odd if 2 does not divide n. But really what I want to talk about is the division algorithm for a second here. So remember, a and b are just any two integers, and it turns out there always exist unique integers q and r, such that b is equal to a times q plus r. Okay? And more importantly, r is between 0 and a minus 1. Okay? So for example, right, let's say b was equal to 17 and a is equal to 3. Okay? Now 3 does not go into 17 a perfect number of times, right? But we do know that 3 goes into 17 at least 5 times, right? So if we pretend like this is elementary school, we would say 3 goes into 17 5 times. 5 times 3 is really 15, right? And then 17 minus 5 is 2. So 3 goes into 17 5 whole times, and we have this remainder value of 2. Remainder of 2. Now 5 is called the quotient, so we'll let q be equal to 5, and 2 is called the remainder, so we'll let r be equal to 2. And this is exactly the same q and the r we have for the division algorithm. So this says basically that 17 is equal to 3 times 5 plus 2. Right? Filling in that my b is 17, my a is 3, my q was 5, the number of times that 3 goes into 17, and my remainder after dividing by 3 is 2. Okay? So we can do that with any two integer values. Right? So for example, here I have a is equal to 7 and b is equal to 30. Well, 7 goes into 30 4 times, so 30 is equal to 7 times 4, right? But it's still a little bit too small, right? So we have 2 left over, right? Remember, your remainder will always be strictly less than whatever value you're dividing by. So we're dividing by 7 here, right? Our remainder will be less than 7. So it could be 0, it could be 1, it could be 2, 3, 4, 5, or 6, but it cannot be 7. Okay? Okay, so here's some notation for us. Q, remember, is the number of times that a goes into b. So Q will always be b divided by a, rounded down. This is the floor function from the last test, if you'll recall. Right? So Q is always b divided by a, rounded down. And so we have this alternate notation here. 30 div 7 is exactly this value right over here. Right? It's 30 divided by 7 rounded down. It's the number of times, the number of whole times that 7 goes into 30. Okay? So our Q is 4 here. Okay? And then our remainder is this notation, 30 mod 7. Mod is short for modulus, which means a small part in like Latin or something like that. And so this is the small part that's left over after dividing. And so that's why we have 30 mod 7. Okay? And so we'll be using these notations a little bit here. Okay? Now, we care about this because it turns out to be super important to find the greatest common divisor of two integer values, especially for internet security. So given two integers, right, what is the largest divisor of both those numbers? So it's a number that divides 1020, for example, and divides 732. And it has to be the largest number that divides both of these things. It turns out to be equal to 12, right? And one way we could do that is by getting the prime factorization of the two numbers. And then we see that, okay, well, 2 squared goes into both of these. 3 also goes into both of these. So then 2 squared times 3 has to go into both of these. But of course, 2 squared times 3 is 12. So that's your greatest common divisor. That's one way we could find the greatest common divisor of these two integers. However, there's a better way, okay? And this result will be used in finding this better way of finding the greatest common divisors, okay? So if a and b are any two integers, right, and let's just suppose a is less than b, right? One of them has to be less than the other one, okay? And let r be equal to the remainder, right, from dividing b by a, right? So this is our notation right over here, recall, b mod a, right? Okay, so it turns out that the greatest common divisor of these two large integers, a and b, is exactly the same thing as the greatest common divisor of, well, these two smaller integers. Remember, a is already smaller than b, right? And the remainder, after dividing b by a, remember that the remainder is always strictly smaller than a, right? So now, right, yeah, we could find the greatest common divisor of a and b directly, but remember, these could be two potentially large numbers. So it's better if we work with smaller numbers, okay? It's easier to find the greatest common divisor if we have smaller numbers to work with. And so that's the advantage of using this, okay? So let's try an example here, right? Let's find the greatest common divisor of 1020 and 732 again, right? Well, let's find the remainder of 1020 and 732, right? And how do you even find the remainder anyway? Well, we have to first find 1020 div 732, right? Remember, that's our Q from the division algorithm. So 1020 div 732, that's just 1020 divided by 732 rounded down, right? Which of course is just 1, right? We could plug it into a calculator, right? We could round it down manually, right? So our Q is 1. So then we have that 1020 is equal to 732 times 1, and then plus some remainder value, right? Right? How do we find that remainder value? Well, all we have to do is just solve for it, okay? So if we want to find out what the value of question mark is over here, which I'm going to call r, r is equal to 1020 minus 732 times 1, which turns out to be 288. So my r is 288. So using my last result, the greatest common divisor of 1020 and 732 is equal to the greatest common divisor of the smaller of those two integers and the remainder after dividing by that. So 732 and 288. And they will have the exact same greatest common divisor, right? And so over here you see I say that 288 is the remainder after dividing 1020 by 732. Okay? So I've went ahead and computed that. All right. But those numbers are still kind of big, so let's do this again, right? We'll find the remainder after dividing 732 by 288, okay? So we can do that. So our Q will now be equal to 732 div 288. And we have to say, okay, well, how many times does that go into that, right? And then we have to round it down, right? So 732 div 288. Let's get a calculator out and find out, right? So I believe that would be 3. 3 times? That might even be too big. I think 2. 2 times, okay? And so now if I want to find my remainder, right, 732 mod 288, right, that will just be equal to 732 minus, right, so remember we had to solve this equation basically, so it's going to be minus a times q. So it's going to be minus 288 times 2, okay? And we do that and we get 732 minus, well, this is going to be equal to 576, right? 732 minus 576 turns out to be equal to, well, let's see, 732 minus 576 I guess I can't do this one in my head. I will get my calculator out here. I don't know if that will show up on the screen here, but I'm definitely using my just plain old calculator here. 732 minus 576 is 156. Alright, so this is going to be equal to 156. Alright, so that's my remainder after dividing 732 by 288. So then the greatest common divisor of 732 and 288 is the same thing as the greatest common divisor of 288 and that remainder value. Okay? So here's where I computed that 156 is the remainder after dividing 732 by 288. Okay? Now we're just going to keep repeating this process, finding the remainder of those two numbers, which turns out to be 132, and then the greatest common divisor of 288 and 156 will be the same thing as the greatest common divisor of 156 and 132. Then we find the remainder of those two, which turns out to be 24. So the greatest common divisor of 156 and 132 is the same as the greatest common divisor of 132 and 24. Then we find the greatest common divisor of those two, which turns out to be 12. So then the greatest common divisor of 132 and 24 is equal to the greatest common divisor of 24 and 12, right? And at this point, you could probably do this in your head. 12 goes into 12, and 12 also goes into 24. And that has to be the largest integer, since one of these numbers is actually 12, right? So then the greatest common divisor of 24 and 12 is actually 12, which is also the greatest common divisor of 1020 and 732. Okay? So that's the way that this is going to work using that result. Now, if we could put some kind of algorithm, right, that would be really helpful. So this thing is called the Euclidean algorithm, and it does basically the same process that we just did. Okay? So here's a procedure called the Euclidean algorithm. You plug in two integers, a and b, where I'm going to say, let's suppose a is smaller than b. Okay? So while a is not equal to 0, so the value of a is going to be changing in this, right? We have an a that we're putting in, right? But we're going to change that value of a throughout the program. So eventually a will be equal to 0, and this condition will be satisfied, and we'll be done with the loop. Okay? Right? So while a is not equal to 0, then we're going to store the value of a temporarily in this variable t. Okay? This is just some temporary variable just to store whatever the previous value of a was. Okay? And then now we're going to redefine a here. So here's where we're changing the value of a to be the remainder after dividing b by a. So this a right here is actually our remainder value. Okay? And then now we replace b with the old value of a. Okay? Fair enough. And then now we do the loop. We say, well, okay, well, now is a equal to 0 after changing this value of a. Now do we have a equal to 0? If not, we do the same process again, right? And then we say, now is a equal to 0? And we keep doing this, and eventually a will be equal to 0. And once that happens, b will actually have the greatest common divisor stored in it. Okay? So let's try it with the same example that we had over here, 1020 and 732. Right? So here I have a equal to 732, b is equal to 1020. Right? So starting off, we have a equal to 732, which is definitely not 0. Right? So then this condition is satisfied right here. A is not equal to 0. Right? So then I'm going to store into t the value of a. So t is equal to 732. Okay? And then I'm going to replace a with the remainder after dividing 1020 by 732. So I have these backwards. I apologize for that. I'll fix this in the coming video. It should be 1020 mod 732 is 288. Right? Same thing with all of these. These values are swapped. These values are swapped. These values are swapped. And these values are swapped. And these values are swapped. I apologize for that. Okay? Now, after computing that remainder value, that's what's going to be stored in A, and then B takes on the old value of A, which was 732. Right? So that's why we needed that temporary variable to store what was in A, so that we could let B be equal to that. Okay? All right. So then now we go on to the next step. So my A is 288, my B is 732. Right? So A is equal to 288, which is not equal to 0. So we still do the while loop. We're still inside of it. So then my t takes on the value of a, temporarily stores it. Okay? My a takes on the remainder after dividing 732 by 288. Right? So that should be 732 over here, mod 288, which is 156. And then b is going to take on the old value of a, which is 288. keep on going, right? My A is 156, which is not equal to 0. Do the same steps again. T takes on the old value of A, which is 156. A is now the remainder, 288 mod 156, which is 132. And then B takes on that old value of A, which is 156. Okay, keep on going. So A is equal to 132, which is not equal to 0. So then T takes on the old value of A, which is 132. A becomes the remainder after dividing, so that should say 156 mod 132, which is 24. Okay, and B takes on the old value of A, which is 132. Keep on going. So A is equal to 24, which is not equal to 0. So then T becomes the old value of A. A becomes the remainder, which is 12, right? So that should say 132 mod 24 equals 12. And then B takes on that old value of A, which is 24. Keep on going. So A is equal to 12, which is not equal to 0. T takes on that old value of A, 12. And then A is 24 mod 12, which turns out to be equal to 0 because 12 goes into 24 perfectly. There is no remainder, right? So now A is equal to 0, and B takes on that old value of A, which is 12. Now we go on to the next step. Now A is equal to 0. So we go back to our program over here, and it says, well, if we should only execute this stuff while A is not equal to 0. So once this condition is not satisfied anymore, once we have that A is equal to 0, now we break out of the loop and we return whatever value stored in B. So we're returning the value stored in B, which is 12. That's your greatest common divisor. Okay? And that's the way that the Euclidean algorithm